First of all, let me thank the organizers for bringing everybody here and thank everybody for coming here. It looks like it's going to be a great meeting. I will talk about my interpretation of what anti-diffusing means. It's a strange word that maybe everybody has a different idea. So for me, it means negative eddy viscosity, and I interpret that as an inverse cascade. I'm going to present a work that has been reviewed in these two papers, and it involves the work done by many people that I have collaborated with. And it's about how large-scale energy structures form. So let's start from the beginning. The basic motivation is that in nature, we often see flow dynamical structures that are of size that are much bigger than what it's forced. And they are coherent and they stay there for a long time, and it's against what we are taught about how three-dimensional turbulence should behave. And the question is, why do these structures form, and why are they so stable and persist? So there has been a number of papers in high-ranking journals in the past years where they indicate that such organization is due to an inverse cascade of energy. So energy somehow manages to move to larger scales and create these large-scale structures. So how things are measured. So this is an example of paper by Jung and Reed, where they took images of the atmosphere of Jupiter. It's consecutive images, so they could construct the velocity field. From the velocity field, they could construct the energy flux across wave numbers. And they would, I had a pointer. Okay. And they could construct the flux across wave numbers, and they could see regions in wave number space that is positive and regions in wave number space that is negative. Negative implies energy is transferred from small to large scales, while positive from large to small scales, or larger wave numbers. So the two processes seem to coexist. This is another example where people actually flew in the boundary layer of a hurricane and took measurements of the velocity, and by that they constructed the third moment, the third order structure function, which is a quantity that's proportional to the flux. And depending on where they were in the layer, they could get positive slopes or negative slopes, indicating that some regions behave in a way that they cascade energy to larger scales, and some regions behave as if they cascade energy to smaller scales. A much safer way of doing that is to do numerical simulations, and this is the result from a work we did with Pablo Minini and Rafael Marino and some students, Andrea Van Kant, in a very anisotropic domain of rotating and stratified turbulence. And it was called resolutions of 12,000 squared times 384. And the forcing here was of the size of the box size, so very small scale. And you can see that much larger structures have formed. And at the same time, if I zoom here, you will see that there are these layers of even smaller scales. And if you even zoom even further, you will see that there are some turnover events, like a Kelvin-Helmholtz instability. So even smaller scales are created. So this image already indicates the coexistence of a mechanism that transposes energy to larger scales and a mechanism that transposes energy to smaller scales. So you can be more precise and construct energy spectra, like on the top here, where we can see two power laws with k to the minus 5/3 slope, indicating the inverse cascade and the forward cascade of energy. And we can construct energy fluxes, as I showed you before. At large wave numbers, it's positive, cascade energy goes to smaller scales. At small wave numbers, it's negative, energy goes to larger scales. And if we go in the two-dimensional plane of perpendicular wave numbers and perpendicular wave numbers and parallel wave numbers, we get a complex transport of energy across these wave numbers. The path that energy follows is a little bit complex. But I don't want to focus on that. I'm rooting for simplicity, so I'm going to choose the simplest possible model that has this kind of behavior of a bidirectional cascade, and that will be the thin layer. So I'm forcing my system in a layer that has a very thin height. And I'm going to vary this length scale and see how the energy changes directions. So this is what we expect to see. An energy flux spectrum that is positive at large wave numbers and negative for small wave numbers, or negative for large scales. And energy will be injected somewhere in the middle. The ratio between that and that is what we are looking for. So the ratio that what fraction of the energy that I'm injecting in the forcing scale goes to large scales and what fraction goes to the smaller scale. So let me sum up the phenomenon that we want to follow. We have a system and we have a parameter lambda. I'm going to be calling it lambda. So it's essentially the thickness of the layer, or one of the thickness of the layer, that I'm going to vary. And the system will transition from a behavior that is like 2D, where all the energy cascades inversely, to 3D behavior, where all the energy cascades forward to the small scales. And in between, there is a possibility that we go through this bidirectional state, where some of the energy cascades inversely and some of the energy cascades forward. Already one can put the question, is this possible? I mean, it is observed, but one can argue that, okay, you don't have enough resolution, you don't have big enough Reynolds number. If you did, then this behavior could not exist. And possibly one can say that this could not exist because how can the same system know to cascade energy to larger scales and to small scales at the same time? And the answer to that it can be possible. One can argue that it can be possible because if you have an energy injection somewhere in the middle, here, and this nonlinearity will diffuse this energy to slightly larger and slightly smaller scales, then if you reach small enough scales, if energy reaches small enough scales that 3D dynamics take place, then that will give a finite flux towards the small scales. And if some of the energy reaches large enough scales that 2D dynamics take place, then that energy will follow 2D dynamics and cascade inversely. So let's go back to the system so I can define everything precisely. So this is my system. I'm forcing at some length scale L in. The height of the box is h. I have viscosity to dissipate energy at small scales. I will add a drag coefficient on the horizontal scales to dissipate energy at the large scales. And I'm going to fix the energy injection rate to epsilon in. So these are all my dimensional input parameters. This is a setup investigated by Leslie Smith a long time ago, and then Antonio Celani followed more recently. So in non-dimensional variables, we have this lambda parameter that I'm going to keep in all the rest of my talk, which is the height, the forcing scale divided by the height of the layer. And we have three more parameters: a Reynolds number based on the drag coefficient, and the box size, normalized by the forcing length scale. I want all these three to go to infinity. So I'm interested in the limit of Reynolds numbers being infinity, and I want to see how the system changes as I vary this parameter lambda in the limit that this happens. So I should first take these limits and then start varying the parameter lambda. Of course, there's a difference in the order of the limits I can take. So if I take the Reynolds number first to infinity, no, if I take the box size first to infinity and then the Reynolds number, then at some point the drag force that I have will stop the inverse cascade, and I will have a finite flux from that length scale to the forcing length scale, and the behavior will be turbulent with a constant flux and power law behavior for the energy spectrum. On the other hand, if I take the limit oppositely, so I first take the Reynolds numbers to infinity, both Reynolds number to infinity, and then I take the large box to infinity, then dissipation will not be effective to stop the inverse cascade. It will hit the size of the box and a big condensate will form. Okay, these two different behaviors are very different and they need to be treated differently. Okay, and that's what I'm going to be doing.
Sorry, before you continue,
what
is alpha in this?
Alpha is the drag coefficient here.
There, okay. And also, how are you doing the forcing? Are you just forcing columnar modes, or are you forcing the vertical velocity as well?
Like this. So it's eddies like this. Okay. So two-dimensional eddies randomly, not so well-oriented like that, but only the two-dimensional component. Okay, so we have these two different limits that we need to keep in mind when investigating, and that leads to two different quantities that describe the state of my system. So if we're in the inverse cascade regime, we'll have this Q alpha, which measures the rate that energy is dissipated at large scales to the rate that I'm injecting energy, or the equivalent for the small scales, dissipation at small scales divided by the dissipation, the energy that I'm putting in. So the sum of the two has to be equal to 1 at steady state. So whatever I inject is equal to whatever I dissipate. So in this case, this is the quantity these are the two quantities I'm interested in knowing how they behave as I vary my parameter lambda. In the other limit, where I have a condensate, what would be better to investigate is the amplitude of the condensate. So how much energy there is in this condensate. So I can define a large-scale velocity field, large-scale velocity energy, by truncating, for example, in Fourier space and keeping only the small wave numbers. And in this case, I want to know how this Q alpha again changes as I vary this parameter in this limit of always. Okay? So now we can start asking questions. So we have this order parameters, what I call, and that describe the state of my system. And I want to know how they change as I vary the parameter lambda. I know that in one limit, lambda equals 0, it should have 3D behavior, so no inverse cascade. No inverse cascade also applies in the limit that I have taken already the box size and the Reynolds number to infinity. That makes only sense there. And then as I vary lambda, I should reach another state where lambda is very big, which will be the two-dimensional case. So everything is flat, and it should behave, all the energy should cascade inversely. So this transition could either happen smoothly, it could remain here 0, then at a critical point, you start cascading inversely. And another option is that you discontinuously go from one state where you don't cascade inversely to a state that you cascade energy inversely. So I'm following statistical phases, I'm going to call them smooth, second order phase transition, and first order phase transition. In the last two cases where there are critical points, I can also talk about phases, where the title of my talk comes from. Because I can say here where I don't cascade inversely, I have one phase, and once I start cascading inversely, I have a different phase. Or I have a condensate or not a condensate. Okay. As I change my control parameter going from the 3D case to the 2D case, I can possibly meet two critical points. One, where I go from no inverse cascade to the beginning of an inverse cascade, to the split cascade or bidirectional cascade, and the other going the other way around from two-dimensional dynamics crossing into the bidirectional, the appearance of three-dimensionality here. So that gives me two different critical points that I want to know the behavior near them. And I have two different limits on the drag coefficients and the box size that I can take. So that gives me four different cases that behave very differently, and I would like to talk to you about this today. So I'm going to start with the first case. So we are here. We are a 3D turbulence. We start to make the layer thinner, and then at some point we cross these critical points and we see an inverse cascade. So this is a figure from Antonio Celani, Musacchio, and Dario Vicente, where they did simulations of exactly what I described. Their forcing wave number is here. They got an inverse cascade like 2D turbulence for smaller wave numbers, then something steeper like entropy cascade in higher wave numbers, and this is where the thickness of the layer is, roughly, and a transition was observed there, going back again to the k to the minus 5/3. Okay, so the idea is like this. For scales larger than the height of the layer, we have 2D dynamics. So we have inverse energy cascade, a forward entropy cascade. And for smaller wave numbers, we have 3D dynamics where energy cascades forward. Of course, if you have an entropy cascade, there is some energy that's dragged along. And we can calculate how much energy reaches here by, okay, we have a prediction for the spectrum here, we have a prediction of the spectrum here. If we impose continuity here, we will get that the rate of energy cascade is 1 over kh squared of what was put in there. So we have this prediction on the dependence with the lambda square. So that's a smooth transition. So as I move, if I make my layer thinner and thinner, the rate that energy cascade to smaller scales becomes smaller and smaller and smaller. So in principle, at least until we meet the Kolmogorov dissipation length scale, decreasing the thickness of the layer smoothly decreases the rate that energy cascade to larger scales. So if this is happening here, one can ask, can we also do the same thing here? So in principle, we can say if the layer is thick enough, then at scale larger we have 3D behavior. So forward Kolmogorov here, some thermalized spectrum here, and an inverse cascade here. I can again match the two spectra, and I will get again a power law, which will also indicate some smooth behavior. So that would kind of indicate that there is no critical point here. However, if one goes here and calculates the rate that the 2D motions cascade inversely and compares that with whatever interactions you have with the force scales, one will find that these guys will win. These guys will win because they have higher amplitude, higher gradients, so they cannot, the 2D guys cannot compete with them. So this picture, actually it's wrong. We cannot say that we can split our domain in 2D dynamics and 3D dynamics, because right here, the interactions are with the 3D modes, not the 2D modes themselves. And that opens the possibility of having a critical point right there. Because if you are far away, then maybe no inverse cascade can happen, because the interactions are with these guys and not with the local guys. So let's go to numerics. This is the energy flux as we vary the parameter lambda, and indeed as we make it smaller, it becomes smaller and smaller and smaller. And if we decompose the fluxes into the part that comes from the 3D motions and the part that comes from the 2D motions, we see that these two processes compete, and they are far away from the mean flux that we get. So there are these two processes, and now I'm going to show you the value of Q alpha, which is the quantity that tells me if I'm cascading inversely or not, as a function of lambda. We do get a smooth-looking curve for a box size that is 8 times big, but I won't take to that limit. So we repeated the same runs at an even larger value of an even larger box size, the thermodynamic limit if you want, and that curve becomes steeper. And if I keep doing that, it becomes steeper and steeper, and seems to converge to a critical point. So if I zoom in and really see that this looks like it's critical. So there is a critical point where this transition takes place. So if I go to real space, I hope this movie now plays. Okay, this is the vorticity of the 2D flow. So you see that two ideas that you are used to seeing in a two-dimensional turbulence, but at the same time you can see at some regions in space that you get a distraction of the eddies, so like this over here, and there was another one somewhere here. Now there it is. And it completely shreds that two-dimensional eddies, and that's the effect of 3D. You don't see that in two-dimensional turbulence. This is clearly the effect of the three-dimensionality of the flow. So that's something that possibly could be modeled by predator-prey dynamics, where you have the 2D eddies being the prey, feeding on the forcing, and then three-dimensional eddies are the predators, where they extract energy from two-dimensional eddies. But that's as far as we have gone on that. And yes?
Can I just ask, so did you see any hysteresis in that transition?
No. No, I mean...
So it's not a first-order transition?
It's a second order. It looks like a second-order phase transition. We saw hysteresis, but it will come later on.
Sorry.
So let me go to the second critical point that we see here. That appears, of course, when the layer is of the order of the Kolmogorov thickness. And if I plot the dissipation due to the 3D eddies as a function of my parameter lambda, I get curves like that. So the larger the Reynolds number, so different lines are different Reynolds numbers, the larger the Reynolds number, the further away it is, which is what we expect because it should scale with the Kolmogorov length scale. And if I normalize by that, the Kolmogorov length scale for 2D, so that's the square root of Reynolds number, all these curves collapse, and they collapse, and they look that there's another critical point here. Of course, you can argue, why do you say it's a critical point and it's not a smooth transition? It's not, because we can prove it. And Basil, we sit somewhere among you, was the first one with Charles Doring to prove that. That indeed, if you're far away on this side, all three-dimensional perturbations will die off exponentially. So I know that somewhere here there has to be a critical point. And if there is a critical point, it has some power law exponent for the deviations from it that scales with an exponent larger than 1. It's clearly larger than 1, and we need to explain how that comes about. So if we look at the energy of the three-dimensional perturbation as a function of time, we see these bursts. And these bursts are the reason for this burst that we see here, some region with no action at all, and then some sudden burst, is from the fact that if the three-dimensional energy is very small, it's being advected linearly by a chaotic field, a turbulent field. So at some times in some regions in space it grows, and at some times it decays. So that kind of systems have been investigated in the past, and it's called on-off intermittency, and they're typically modeled with equations like that. So we have an amplitude, it changes with some linear growth, plus a noise part, noise because we have turbulent dynamics that drive the instability, and a saturation. And if I look at this equation in logarithmic space, I get that the logarithm of A follows a random walk plus a drift. And this is what causes these wild variations of the energy as a function of time. Of course, that gives a prediction for the moments that scales linear with my deviation. Mu is lambda minus c. So we saw an exponent larger than 1. This predicts an exponent that is 1. So there's something more to it. So this is results from numerical simulation at the top. It shows the energy of the three-dimensional perturbation. And from left to right, I'm approaching the critical point. So if I'm far away from it, three-dimensional energy is everywhere. As I move closer, we see patches of no action, no activity, and smaller and smaller. And if I'm really close, I see very isolated patches of 3D turbulence. So as I move from left to right, not only the amplitude is decreasing, but also the fraction of space that it occupies. Below is simulations of the model that I wrote before, which is what I wrote before, plus a diffusion tape. So now A depends also on space. So we have the linear instability with the noise, which is now delta correlated in space and time. We have the nonlinearity, and we have a diffusion coefficient. So these kind of models were done in the end of last century. There's Chu and Genovese and Munoz that have worked a lot on that. And they see this behavior. The two figures look quite similar, if you forget the discretization that you see here, because it's a much smaller resolution that you need for that. And there are predictions for these models as well. So these predictions are that the first moment scale is like 1.14 something. These are calculated numerically. There's not exact theory for them. And the second moment scale is like 1.7. Second moment is the energy. So they are defined here. This is the data from the numerical simulations, and these are the fits that we have. That is the square root that one expects from a typical ordinary bifurcation. This is in the case we have extensive noise. And the fitting is reasonably well. So we get two new exponents that describe the instability close to that threshold. Now we move to the third case, where I'm going to be answering the question of Edgar as well. So we are in the case, let me repeat, that the box size is finite, so it's big, but the Reynolds number is much bigger, so we get a condensate. Dissipation at large scales cannot stop the inverse cascade, so we get a condensate, and we want to vary the parameter of lambda to go from three-dimensional behavior, no condensate, to its appearance. So we go ahead and do that, and we get points like that. That's the energy. That's my parameter lambda. And as I vary, I get, well, for very small values of lambda, no condensate, energy is almost 0. And then at some point, I switch to a different behavior. And here it seems that a small jump exists. So we went in more detail and followed that, and we get a hysteresis diagram. Hysteresis diagram means that we start with a small value of lambda. We let it saturate. We use that as initial conditions and increase the value of lambda, and so on and so on and so forth. And at some point, we see the energy jumping to a condensate state. And then if we use that as initial conditions and start to decrease the value of lambda, we get a jump to the 3D behavior, but at a different point. So I can have a hysteresis loop over there. That's all fine, that's all well. But one can ask the question, did you wait long enough to be sure that if you're here, you won't jump there? And did you wait long enough here to be sure that you won't eventually jump there? That's a very valid question, and it's very hard to answer. So this is how we go about it. For every value of lambda that we have, we start with some initial conditions. We wait some time, and then we see that it transitions to the condensate state. So we start from 3D turbulence, no condensate, and at some point we see a transition to the 3D state. Then we repeat the run with some different initial conditions, so noisy initial conditions. And we see a transition at a different time scale. And we repeat that, and we repeat that, and we repeat that, so that we get enough times to compute a histogram of the distribution of times that we meet. So this is the probability to transition at the time t. And we do the same thing from the other side. So we start with a condensate, we let it run until it decays, and then we repeat with different initial conditions, and repeat and repeat and repeat, so we can construct. And we see that these time scales are exponentially distributed. So exponentially distributed means that it's a memory process, and that it has a finite mean time. So we can calculate the mean time now, after repeating that many times, of the mean time scale to transition from one state to the other. And if we plot that, we get diagrams like that. Now, I note here this is a logarithmic axis, while this is linear. So this is a curve that curves up. So it's something that goes faster than exponential. So this is the time to decay. So that means that we start at some point, and around this value of time, it will transition to the other state, from the condensate to the three-dimensional turbulence. Then we increase the value of lambda. It takes longer, it takes longer, it takes longer. And on the other side, we start from the three-dimensional turbulence. It jumps to the condensate, and the smaller value of lambda, the longer time it takes. If it goes faster than exponential, one could possibly interpret that as a singularity. Singularity means that it diverges, so there is no transition to the three-dimensional case on this side, and there is no transition to the condensate state on this side when lambda is too small. So to see if that works, we took those time scales, mean time scales, as a function of lambda. We plot the inverse of them and raise them to some power. This becomes straight lines. And then we can extrapolate and see where they hit the zero value of that. So 0 means that if I am on that side or the other side, only one transition takes place. So if the big question is if they cross each other. If they cross each other, like here, which is for a small value of the parameter, I think this is lambda. Reynolds, that's for a small Reynolds number. So if they cross, it means that if I am between these 2 points, I will keep jumping from one state to the other. If I wait long enough, I will jump from one state to the other. While if we are in this case, where they don't cross, it means that if I sit right between those 2 points, if I start in one state, I will stay there. And if I start in the other state, I will stay there. So that permits us to draw diagrams like that, where I have 4 columns here. The orange like one is where the 3D state is stable. The parameter here is the size of the box, and here it's the Reynolds number. So here it's the 3D turbulence state if I'm in this region. Here the condensate state is the only stable point. This region between is what I call a bimodal state. So the system jumps from one state to the other and back and forth if I wait long enough. And then we have this little triangle here and this little triangle over here, where if I start in one state, I will stay there. And if I start on the other state, I will stay there. So they're both stable. I should explain here, because statistical physicists usually complain at this point, that the claim that it will take infinite time to jump from one state to the other, maybe it's not possible, because once you have noise in the system, if you wait long enough, it might jump. It's true, but that would require a better model than just assuming singularity. That's why we haven't followed on that direction. If there is a better understanding of how these transitions takes place, then maybe we can reach in a model that is more sophisticated, that would involve exponentials of exponentials that lead to these transitions. Okay, so that takes us to the last case. So here we are at this point. So in this case, we are, well, let's start from the left, 2D dynamics. So the flow is exactly 2D. And then I start increasing the layer. It forms a condensate. And then I start to increase the layer. At some point, three-dimensionality appears. So this is the results that were made by Basile, Gallet, and Kanambiran Seshashayanan, where they did exactly that. In this case, they also had the rotation, but then never mind for the time being. That's the same true for thin layers. So they get the big vortexes one usually gets in 2D, and then one observes three-dimensional instabilities that are both very localized in space and also small amplitude. And if you look at the energy of 3D, the 3D part of the flow, it gets behaviors like that. The flow slowly decays for some long times, and then suddenly, very few turnover time scales, it grows by hundreds of orders of magnitude. This is the log, and it goes from something like of the order 10 to 300 or 400. So you have these very extreme events.
Alex?
Yes?
Can you just give some indication of where that three-dimensional instability comes from with respect to the
Well, my understanding is somewhere where the strain is bigger in the flow. Basile and Kana were doing this investigation, so they would be more suitable to answer that question. So, what about this? The problem here is that these are very, very costly runs, because you have to wait very long time to get an extreme event, and to do statistics on that it's not feasible. You have to wait a very, very, very long time. So we did another thing. So we constructed a point vortex model, where the 2D dynamics are modeled by point vortexes that move around the regular point vortex model, and we add to that 3D point instabilities, modes, that are being advected by the 2D flow, and they can extract energy from the point vortices and grow in time. So that is a much cheaper model, and we can run it many times for many times the same parameters. So we can do statistics, and we can get growth rates that look like that, and we can plot histograms of these growth rates. And what we get is that the probability of a given growth rate, the positive part, follows a Pavlov behavior. So if I am to model this as a random process, as we did in the cases before, we can write down an equation like that. We don't need space variation, because these are very local structures. Only the difference now is that the noise here should not be Gaussian. So it should have Pavlov behavior. And if it's a Pavlov behavior, it means that not the Gaussian noise, it should be described best with a Levy process. a Levy noise, if you want. The Levy noise is when you get, it's in the limit when you have many random numbers that have variance that is not finite, then the probability of their mean value after many iterations converges to these different probabilities that depend on two parameters, alpha and beta, and that gives the behavior of the probability as they grow, and it's a power law probability. So the alpha and the beta is some parameters that we need to input in the model. Now the important thing is that once we do that, we get new predictions for the deviation of the energy as I move away from the critical point. There are new power law exponents that depend on all three parameters, alpha, beta, and nu. Nu is the order of the n is the order of the nonlinearity. So a new set of parameters has been calculated, and this was done in a paper by Andrea Fancan and François Petrellis. And we reach at the end of my talk. So we had these four different cases on a very simple system. And we saw pressure-rate dynamics. We saw extensive on-off intermittency, which had led to some new exponents, hysteresis and rare transitions, and Levy on-off intermittency with another set of exponents. So to conclude, is that the phase transitions in turbulence showed a richness that I was not expecting when I was starting this. It showed a richness that is beyond what I thought. I had to learn a lot of new things to go through that. And my take-home message is take a system, simplify it as much as you can, and push it to its limits, and new physics and interesting things will come up. And with that, I'll finish my talk, and thank you very much for your attention.
Thank you, Alex, for a wonderful survey. So, Grisha, as promised.
Thank you. Thanks for this comprehensive review. Mostly numerics. There are also experiments which could tell you some things which numerics couldn't observe because nature computes faster. And there was this nice experiment about Schatz's group where they really seen it's called upscale energy transferencing layers, which means it's exactly your subject. That spontaneously appearing large vortex can totally rearrange three-dimensional turbulence and produce inverse cascade, even at lambdas where, according to the diagram, you would not see any two-dimensional thing. David Byrne, who actually did this.
This paper?
But this is something which is kind of relates to your diagram. It means that you can kind of numerically, like what Celani seen, you numerically see that when your lambda passes through 1/2, then you don't see inverse cascade. If you wait long enough, you experimentally see that you can see inverse cascade because some condensates spontaneously appear. Would it change the diagram, or just something which like flux in this things?
Here's the thing. You have to take the large box limit and the large Reynolds number limit. So I don't know if that would survive if you really do that. Because yes, you do see some events that go there, and if you are close to the transition point, things can happen. But what I'm interested in is in the limit that the box size is going to infinity, and the real numbers go to infinity, and then I start varying the lambda. So I don't know exactly if that falls in that range or not. What you described.
What I'm trying to say is that in numerics, Celani runs. It's really was very long run, and it seemed like there is no inverse cascade. When we do experiment for this exactly time that numerics for run, we see no inverse cascade. But we can do experiments like 5 times longer, and then we see appearance of the vortex. What I'm saying is that there could be a very long-lived metastable state, which you also studied. So this is something where I would be very hesitant to drive diagram, which we usually drive for system like stable forever. This is the phase state forever. You don't put, or you write this metastable phase like this, and then you quantify.
It's possible. I cannot exclude it because I do have only numerics to test
I
it,
was
but
never able to sort it in this clear terms of phase diagram, but it's definitely some spontaneously appearing flash vortex and totally rearrange three-dimensional flow into locally planar flow, and then you have an inverse cascade where you don't expect it because it's very sick layer.
so yeah, so you probably, since you do form a condensate, you are somewhere around here, yes. So then, yes, in principle, I also do see stuff like that as well. I see no inverse cascade, and then suddenly, it goes. So, yeah.
Rich? Hi, can I ask about a paper you mentioned, Gallet and Doring, two-dimensionalization of a 3D? That was with rotation or?
That was with magnetic field. The first time that they did it, but you can take the limit of that paper B equal to 0 and you recover the hydro part.
Oh.
So the first paper they did it, then it was followed by a paper on rotation by Basile alone.
So that's a regular limit, is it? So they didn't need the magnetic field at all?
They wrote they had a formula for the case of the magnetic field, which depended on the amplitude of the magnetic field. But they could take the magnetic field to 0 and recover the result that I mentioned.
Wow, okay, thank you.
So it's a much simpler result than what they actually proved.
Yes.
So your condensate seem like it's a monopolar vortex or two monopolar vortices opposite side. Like did you consider dipole, like a compact dipole vortex as a condensate and stability of that? Does it?
Well, what do you mean a compact dipole? As opposed
Like a dipole vortex which is like a circular that has two poles. And it also happens.
in my simulations, I do get the dipole. So one vortex here, one vortex here, with the distance separating half the box size.
Yeah, that's not what I
That's
mean.
not what you're talking about.
Because then you model this state as a sort of, to get an ensemble, you model this as point vertices.
Yes.
But you could also model the 2D turbulence state as point dipoles in some sense, dipolar vortices that are moving around. That's also, in some sense, locally they are condensates.
Okay.
In the sense that they are minimal.
Let me ask if I understood correctly. So if you take point vortexes and then you change the temperature of your system, there is one region in temperature where you get these dipoles. Are you talking about this state?
Possibly, yeah.
So we did look at that, but not a lot. So because they were not so much physically relevant. So I don't even remember. Adrian sitting right in front of you probably can tell you more.
Okay.
So there's a question from Anna.
Can you comment on how or if everything changes if you change the forcing, like the scale of forcing, but also if you make it 3D or something like that?
So we have gone through cases like that. So definitely when you change, when you add the forcing that contains also three-dimensional vortices, it moves the critical point further away. So the three-dimensional turbulence is more persistent. It moves it on this side. As when I was forcing only 3D, I couldn't get it yet to have an inverse cascade. I don't know if it's that because I didn't went far enough, but so far I couldn't get it. But then again, you do see inverse cascade in convection, which is essentially 3D forcing. So it should be there, but maybe I didn't go far enough to see it.
And the type of transition doesn't change with if you make the forcing 3D? Doesn't change the type of transition?
I wouldn't expect it, but I could be wrong. One needs to do it to be sure.
Bruce?
So you focus a lot on the horizontal vorticity, but I was curious about the vertical structure. In some cases, like what is shown here, it seems you have coherence from the top to the bottom of the domain, but you did show another case where you saw layers.
Yes.
And I'm just curious, where in this regime diagram would you see those layers appear?
So these layers were was an effect of stratification, which is a more two levels of complexity higher up. So it doesn't exist in this, diagram. If I want to do that, I would need to add two more dimensions, which would be rotation and stratification, and that will make it more complex. And it's something that it's a lot of work needs to be done in that direction. That's me suggesting that.
Right?
Yeah, in case, that was a very nice talk, by the way, thank you so much. In case one, the continuous transition, the second order, did you tell us what the exponent is? That's the first question, but the more important question, did you look at the fluctuations? Is there something equivalent to the susceptibility that you can look at? Did you do that?
So the exponent looks like 1, but I have no theoretical argument to justify that. I'm looking into that, and I have a master student that is trying to look in that direction. But right now, I don't know the answer. But that's something that needs to be looked at.
And that's, you're answering the fluctuation question, or is that also? Have you? Yeah.
I mean, I looked at the fluctuations of the fluxes. They are much bigger than the mean flux, so it's definitely controlled by them. But what I want to do is see how things decay once I cross to the no turbulent, no inverse cascade limit. Well, I don't know about the susceptibility. I'm not sure what quantity I should be looking at there as well. So let me not say anything more.
Yes.
I have two questions really. One comes back on a question about forcing. And if I understand correctly, your forcing is random.
Yes.
Have you tried any other type of forcing that allows for phase correlations to build up? Because I would anticipate that potentially you could have a difference in your type of transition if you allow for phase locking or phase
Okay. So
synchronization.
We have tried constant forcing. The first paper that we did was actually, in fact, with Alexandros and my first student. It was with constant forcing, so we kind of saw something similar. And we tried another type of random forcing, which is not delta correlated in time, but we fixed the injection of energy. And that's kind of a deterministic. It's a deterministic, but we fix some random phases at the beginning, and that's all. It showed the transition like that. I don't know if I could possibly devise some forcing that breaks something and changes the type of transition. But in particular, for that point over there, I don't understand it. I still don't understand it, and I think it's a lot of work needs to be done to understanding. So I cannot exclude that some forcing could change the order of the transition, the type of the transition.
My second question came back to the question that came up before about the physical mechanism of the transition from the 2D condensate to split cascade. Mm-hmm. I mean, physically speaking, you have three processes. You either have vortex thinning that would give you an inverse, that would give you forward or an inverse cascade, depending on the alignment of vorticity and the strain associated with the shear that's generated from stretching, from shearing a vortex, or vortex stretching or strain self-amplification. My question is whether, and I know that you can't answer it because there needs to be analysis done, but it might be an idea to look into that, to measure the different types of processes, and then as a function of increasing your domain size, you will see which one takes over. So one would be that you just have vortex stretching that kicks off, or the other one would be that if you have a different alignment between strain rate and vorticity in vortex thinning. So there are two processes two physical processes that could be taking over. I guess would be it's the vortex. Right?
It's a good direction, yes. I have to admit, it's a good direction to look at.
And would just be post-processing.
Yeah. I wouldn't say it's a post-processing because you need statistics, but it's a good direction. I would agree that it's a good direction to look at. Yes.
Yes.
I'm curious that you described the distinction between 2D and 3D almost like a kind of binary sort of classification that we often find in practice. I think certainly on the Jupiter case, for example, the forward cascade is at scales where the turbulence may be 3D, but it's clearly not isotropic. Does the isotropy of the 3D play any role in what you've been describing?
Well, first of all, I didn't say it's a binary. In fact, what I said that it goes from one case to the other, passing through a state that has both behaviors. Of course, anisotropy plays a role. It's there, and it's what makes the essentially 3D flow, because it's 3-dimensional. We live in a 3-dimensional world. Such anisotropy that makes it behave like a 2D. So yes, it plays a role. Yeah, you need to ask a more specific question to say something more. Otherwise, I can't. So definitely it's there. Yeah, I would agree.
The flux is a tensor, not a vector. It's a tensor. It depends on direction.
Yeah.
So I have a question about your bistable example, where you didn't see any transitions. So is that due to but it's still a noise-activated process. So is that because some special properties of the fluctuations in the turbulent state that is preventing the transitions from? But it's related to Grisha's question, I think.
I cannot explain why it has this behavior. I was surprised. I was expecting that if you wait long enough, you will at some point see the transition.
Of course, it's not Gaussian, so
it's not Gaussian. It shows this super exponential behavior. Super exponential behaviors I've seen before. I mean, in the Quasi flow also sees that. Why it appears? I don't have it. I don't know. I really would like to see if there is a model that gives something more than assuming that it's singular. But at this point, I don't know, and I don't know how to go there.
Are there any more questions? Okay, if not, let's thank Alex again for a wonderful talk.